time to start, and we continue with the second installment of Mykola's mini course on stable envelopes and various months of the year. So that's, with this, I turn it over to Mykola.
Thank you, and thanks for everyone who came. So yeah, I'll continue with the part two. And first recall from the last time that we were talking about is 3D n equals 4 and n equals 2 theories, and particular 3D n equals 4 viewed as an n equals 2 with a special symmetry U1 H bar that is part of the n equals 4 R symmetry. And we put them on an elliptic curve times a real line, thought of as time, and we picked a supercharged Q, which squares to the anti-holomorphic translation in the direction of the elliptic curve. And then we found that the BPS equations, so the configurations in which physical theory localizes, were given by gradient flows for this particular Morse function. And endpoints of the flow were fixed points of the Higgs branch, fixed points with respect to some torus A, which corresponds to flavor symmetry, and that's the which torus is determined by the mass parameter, the real mass that appears in this function. Now, let's continue with this. The question is, can we interpolate between different values of mass in a supersymmetric way? So basically, we want something like this. We want the mass to change somehow in the y direction. Y is the coordinate on R, thought of as Euclidean time. And we want to preserve supercharge. So like want this configuration to be compatible with supersymmetry. The standard physical approach to such questions is to find a supersymmetric background. So you consider a background vector multiplet that's what is called gauging this flavor symmetry. So you add this vector multiplet. Let's call it VF because it's for flavor symmetry. So what does it mean that you add a background vector multiplet? It means that you add things like connection for flavor symmetry and its superpartners that follow from supersymmetry, but you don't integrate over them in the path integral, but rather you just give them certain fixed value. And then the demanding that they preserve supersymmetry is simply saying that the fermions, well, usually we consider bosonic background, so it means that the fermionic fields vanish and Q of them also vanishes. So that's the statement that the background preserves supersymmetry. And well, okay, this vector multiplet, the background vector multiplet, it contains so the flavor connection, so gauge field, and real scalar for flavor symmetry. Then there's also an auxiliary field, as every real auxiliary field that's necessary for some technical purposes. And there are fermions, which in the background they vanish. So the constant real mass, when you turn on in the constant real mass, it corresponds to just giving a constant value to this sigma r. So it's just a certain, and all other fields are just zero. And so it's just a certain standard way to turn on mass for flavor symmetry. So here, yeah, that's this real scalar in the flavor symmetry multiplet. Now, there's actually turns out that there's a simple generalization that allows to vary mass. Namely, you just make this y dependent, and additionally turn on another field. And in fact, such solution preserves more than just one supercharged Q that we're interested in. It preserves the whole 2D n equals 0, 2. So in fact, two supercharges. And if we turn off this SUSY breaking parameter h bar, then in fact this solution preserves 2D n equals 2, 2 supersymmetry. So it's a certain half VPS configuration, as it's called, meaning that it preserves half 4 out of 8 supercharges. To be more concrete, this way to introduce mass when we turn on some background fields, it actually well, I can just write the corresponding term in the Lagrangian. So it's something like this. Well, not something, exactly this, where you have this phi is a complex scalar field. So it's the what was called chiral multiplet. So it's some matter field. And there's a mass term for it. There's also, well, that's part of that mass term, really. There's also superpartners that are fermions, and the mass term looks like this. And then there's this correction due to the position-dependent mass. Okay, so there's such supersymmetric background, and one could ask how much it depends on this function mr of y. In other words, what happens when you start varying mr of y? So if we take mr of y and change it a little bit. Well, it turns out that in general n equals 2 theory, the variation of this mass term, if you do this, the variation of the mass term is non-zero, and in fact, the details of this y dependence are important. But in n equals 4 theory, even if we have this SUSY breaking parameter h bar, in n equals 4 theory, the variation is q exact. So it's a q of something. Plus, there are some other terms, actually. There's some little subtlety here, that there are some other terms which don't vanish immediately, but they vanish under the correlators. I'm not going to go into that. But one has this, as long as you keep mass fixed at infinity. So it means that in this case, for n equals 4 theories, the precise shape of your mass profile doesn't really matter. You can pick certain value at minus infinity, or something at plus infinity, and just interpolate them. And this gives you a unique, because of this Q exactness, gives you unique answer in the Q cohomology. Well, answer for what? For a linear operator that relates you the vacuum at minus infinity to the vacuum at plus infinity. And I remind you that vacuum can be thought of as a, in this case, Q cohomology class for Q acting on the Hilbert space on the elliptic curve. Well, in fact, it turns out that even more, only chambers of this masses matter. Chambers in the space of real masses, which is just the algebra of the maximal torus of your flavor symmetry group. So what are these chambers? Well, okay, well, we can recall from definition from Maulik and Okounkov. that one just take this alpha, real algebra, and remove root hyperplanes, and then what remains is a union of chambers. And here these A roots, according to them, are just A weights that occur in the normal bundle to XA, to the fixed point locus inside of X. Right? So just look to normal bundle to XA inside of X. A acts there in a certain way, and it gives you the set of roots. And from the physical point of view, at the root hyperplanes, some fields, some of the matter fields in your action become massless. So something changes at that locus. Really, the answers usually get some poles due to fields becoming massless. So one just has to choose chambers for the real mass at minus infinity and plus infinity. And then physics provides you with a unique, up to Q exact terms, interface interpolating between this real mass at minus infinity, which is supposed to be in one chamber, and mass at plus infinity, which is in a different chamber. Now, as I just already reminded you, recall that Q cohomology of states which means of Q, consider Q as a linear operator acting on this Hilbert space. It's just the space of vacua. And therefore, what we find in the Q cohomology is that this interface, this changing mass profile, generates you a linear map, let's say, from the space of vacua at this value of mass with this mass turned on, so which corresponds to mass at minus infinity, to the space of vacua with a different mass parameter, plus infinity.
Mykola, question.
Yes?
So, if we kind of do this sort of, this kind of wall crossing, whatever you call it, then its result is unique in 1 and 3 dimensions, but in 2 dimensions, there's some dependence. There's if some elliptic function, depends on what you do with the poles of that elliptic function, you'll have different things in cohomology and in elliptic cohomology, result is unique, but in K-theory, result it kind of depends on some other things. Do you see this somehow? Or is it or this argument is specific to 3 dimensions?
No, this argument is universal to all dimensions, 1, 2, 3. So in 2 dimensions, do you mean this dependence on the slope parameter? Or
well,
something?
yeah, this depends. You get like a bunch of windows, and depending through which window you go, so that depends on your you get slightly different things.
Mm-hmm.
Well, maybe no. Sorry, I'm confusing with this. I apologize. I'm confusing with this with interpolation in this topological variable. There you get a bunch of windows. Maybe okay. So I'll take it back. Sorry.
Okay. Yeah, so in that case, when there's independence, I guess the variable is a complex variable that you're interpolating. Probably.
Yeah, that's right. Yeah, and then
And then you
depending
have
on the phase, you get different things. Yeah.
you can have something in codimension 1. But here, because it's a real variable.
Yeah. Okay. Yeah. Sorry. I was thinking about something else. Yeah, I apologize. Yeah.
All right. Good. So yeah, so this gives you a construction of this Janus interface for mass parameters. But one can also do the same thing for the phi parameters. Recall the phi parameters is something that appears as a constant term in the moment map. And real phi parameter is related to the, real moment map can be replaced by stability condition. There is an analogous construction for the background with a phi parameter that changes in y. And in fact, there's not much difference because a phi term, it can be thought of as a mass, but for the topological symmetry, what's called in physics topological symmetry. So what is it? If you have a U1 gauge field, dynamical gauge field, so the one that you are integrating over in the path integral, you take its curvature and just take it Hodge dual, and what you get is trivial, what's called the topological current in physics. So it's just trivially conserved due to closedness of F. And with respect to this current, the charged particles are vortices. And so then the vortex counting parameter would it's like a Kähler parameter, but what's called Kähler parameter. I mean, it's related to Kähler parameters of your Higgs branch. So one can do analogous thing and construct the background with a phi term that changes in y. And in this case, I can also write you an explicit Lagrangian. It's much shorter, well, just slightly shorter than in the mass case. And it's actually simpler because even in n equals 2 theory, there's deformation of the profile of the phi parameter is Q exact. So this deformation of Lagrangian is Q exact as long as I keep the phi parameter fixed at infinities. So again, it gives you unique up to a Q exactness interface that also depends on chambers, but now in the algebra of this torus of topological symmetries. And again, I assume that at minus infinity it takes value in one chamber, and at plus infinity it takes value in another chamber. And it gives rise to another Janus interface, which also can be thought of as a linear map between vacua at different values of the phi parameter. So in the end of the day, we have two such maps. One is the one that interpolates between masses. I'll call it J. And the one that interpolates between the phi parameters. Recall, I think I explained it last time. Maybe I didn't. But the Higgs phase of your theory corresponds to the range of parameters where you keep the mass 0, the real mass 0, while the real phi parameter is non-zero, generic, and large. And the Coulomb phase is the opposite thing when you keep the phi parameter 0 and the real mass is generic and large. Well, it doesn't have to be large, but really due to the RG flow, like the mass will inevitably grow in the IR, so we can just assume that it's large. And then, so we can just take the following thing. I can take the mass Janus between the 0 mass and some mass R, and a phi Janus between some value of a phi parameter theta R and 0. And then, well, what I get is a product. So this product is the interface that interpolates between the values of parameters that correspond to the Higgs phase and those corresponding to the Coulomb phase. So I can think of it as a phase interface between the Higgs and Coulomb phases. But then really, the claim is that this part that interpolates between zero and non-zero mass is really going to be a stable envelope for the Higgs branch. And it can be understood in terms of the BPS equations in the original theory, because as I said, it's gradient flow equations, and like that connects to the original definition of the stable envelope. And it's like interesting in the Higgs phase. But this should be the same thing, but for the Coulomb branch. And it's going to be interesting in the Coulomb phase of the theory. But in the Lagrangian description of your quantum field theory, there's a certain asymmetry between Higgs and Coulomb phase, even though like the actual theory, like if you think about it, say about the conformal theory that you get when you look at it at large distances, it's symmetric between the like in the operator description, like when you work with operator value distributions and you write some OPs, operator product expansions between them. That's how people think about it in conformal theory. Then of course there's a complete symmetry between these Higgs and Coulomb branches, and that's the
That's this mother function or duality interface of this object, right?
yeah, that's right.
Okay.
Yeah, so the complete symmetry, but in like the mirror symmetry, right? But in the Lagrangian description, it's just the artifact of Lagrangian description. There's no such symmetry, manifest symmetry, and in particular, the BPS equations, they're good for describing these stable envelopes on the Higgs branch, but on the Coulomb branch, like if you want to write similar gradient flow, you would have to go to the mirror description where it becomes a Higgs branch. But also there's one more thing is that this study of Higgs and Coulomb phases and the transition between them, that's really mathematically corresponds to symplectic duality. And this viewpoint on this physical viewpoint on symplectic duality was proposed in really this paper by Bulimodimov, Tagliot, Hilburn 5 years ago, about 4.5 years ago. So the vertex, yeah. So right. So so one can indeed think of it from this point of view. This thing that's you said the duality interface. It's like just the phase transition interface, so to speak. You look at the Higgs and Coulomb branches of your phases of your theory, and in principle, the fact that there's also mirror symmetry, so that there exists another quantum field theory where these two are exchanged, is not, strictly speaking, necessary for this. But then, okay, I will talk more about it soon. Recall that there is this thing that was studied in various papers by Andrei and collaborators on. So there's a vertex function, which is physically it's a partition function on this cigar with an A twist on it, and it corresponds to K-theoretic count of quasimaps into the Higgs branch. So this one fixes vacuum at infinity. This cigar prepares you a state C, and then the overlap is this V alpha. And the set of these V alphas for all vacuum gives you a certain element in the K theory of your Higgs branch. And the fact that this this really counts quasimaps is because there's the BPS equations in this case. One like this, and which tells you that you look at some sort of holomorphic maps, and then there's another one that relates the moment map to the curvature of your Okay, here I mean only the U1 part of your gauge field in the cigar direction. And these are really the vortex equations. And then in the limit where you take e to infinity, the vortices shrink to points and you get these quasimaps. Now, there exists also another background that, which is not A-twisted, but it computes the same thing. And I already alluded to it last time. That's the background that corresponds to this superconformal half index, but you really also have to. Well, usually superconformal half index is discussed with a round half like hemisphere, but it's possible to also stretch it. And in this case, the A-twisted background really only emerges close to the tip of the cigar, whereas at the equator we have this our supercharged Q of interest preserved, and one can use this. No, the claim is that this background also computes up to some proportionality coefficient, also computes the same V alpha. But one can use it to understand what happens to V alpha under the phase transitions, because now in the cohomology of this Q, we have this interface that describes, tells us what happens when we pass from Higgs to Coulomb branch. So, okay, here now in this pictures, I will surprise the circle direction and just draw the cigar. Sorry. So, suppose we look at this in the Higgs phase first. So we look at the cigar with 5 parameters turned on and mass is 0. And this cigar generates as a certain state. Let's call it CH. So C for cigar and H for Higgs phase. But now let's act on it with our interface, which has these two factors, the mass and phi Januses. Now, so the first one just changes the mass parameter only from 0 to some large value. And the second one changes the phi parameter from some large value to 0. And there's some other property which I didn't explain, but one can show that in this cigar background, as long as you keep parameters fixed here, you can vary parameters inside the cigar. And in particular, we can sort of get rid of these interfaces by sort of simply moving them to the left and off the tip of the cigar, and just whatever parameters we have here, we can just sort of spread them to the entire cigar and then get this. And what is this? Well, that's it also generates as a certain state in the Hilbert space. Now the subscript C stands for the Coulomb phase, because now we have 0 Fi parameter and large mass. So this heuristic pictorial argument shows you that if you start with the state in the Higgs phase and then act on it with with our operators, the interfaces, you get state in the Coulomb phase. So this Janus realizes also a phase transition, or like transforms your vertex function and sort of gives you a vertex function for the Coulomb branch, sort of like counts quasi-maps into the Coulomb branch, whatever that means. Now, if the Coulomb branch, so if we have an explicit description of the Higgs branch of the mirror theory, then we know the Coulomb branch is the Higgs branch of the, so Coulomb branch is the Higgs branch of the mirror theory, and then if it admits a quiver description, then it's also given by a GIT quotient. And then the notion of quasi-maps is clear in this case. And we arrived to the fact from Aganagic-Okounkov that these elliptic stable envelopes gives you a transition matrix that relates vertex functions of the Higgs branch of your original theory on your mirror theory. More generally, we could imagine that this XC does not admit a JD description. So you have a theory, but you say don't know how to write its 3D mirror. But still, this picture with phases, with phase transitions still holds because you simply do it in the original theory without passing to the mirror. So it suggests that the interface relates vertex functions of the Higgs and Coulomb branches, but then there's a problem: how to define quasi-maps into the Coulomb branch and how to count them. I mean, that's an open problem. I don't know how to do that. But I don't.
Yeah, I
I'm not
should
even.
say that this is like there's a I don't know how to do that either, but as a formal kind of mathematical point, these are this vertex function. They're solutions of some Q-difference equation, and the ones for the Higgs or Coulomb branch are just mean different analyticity condition for that solution. So if you have on your Higgs side, if you have this Q-difference equation, you can just define the corresponding solutions with the analyticity as if they were for Coulomb branch. That would be the vertex function, and then this kind of theorem would be, somewhat tautological. I think this is, but that's one definition. I mean, not very satisfactory.
Okay, so that's a definition, and perhaps good for some purposes. But I meant like some geometric definition.
Right. I understand. Yeah.
So perhaps doing something with the Braverman, Finkelberg, Nakajima definition of Coulomb branch, maybe one can come up with some definition of quasi-maps into Coulomb branch. And then I can then prove that it agrees with the difference equation point of view.
That is not so easy because, for instance, suppose the Coulomb branch is a point. Right? That point, to count quasi-maps to that, you need to write that point as some non-trivial way, and that's even that's at that starting point is already very non-trivial.
Right.
there are many Nakajima varieties, for instance, there are points. So.
Yeah. So yeah. As I said, I don't know. I cannot say anything useful about that. Yeah, so here I wanted to just add one more point of view on this same discussion, but the one that's probably more sort of closer to what one can find in some physics literature. Namely, if you look at this from the superconformal index or half index point of view, you really look at the theory with zero mass and the phi parameters, and then consider a certain boundary condition here, which is equivalent to fixing a vacuum alpha at infinity, sometimes referred to as a thimble boundary condition, or in the gauge theory context, it's some special not special, what's the exceptional Dirichlet. So this thing, it computes you the half index with this special boundary condition, which is also proportional up to some coefficients, so to the vertex function. And really, this can be thought of as just turning on mass on the right-hand side and then fixing vacuum at infinity. Now, if we do mirror symmetry, this will correspond to the configuration where you have, okay, here, since we had both mass and the phi parameter 0, after mirror, we'll still have both mass and the phi parameters 0. But in this region, since one of them was non-zero here, they switch, and now we have non-zero phi parameters and 0 masses. But then there's a still fixed vacuum at infinity. But in the mirror theory, this, if at least in the case when we have isolated massive vacua, there is a one-to-one correspondence between the original and mirror theory between these isolated massive vacua. But then this configuration using our interfaces can be equivalently written as we sort of add two interfaces here. So instead of going from mass from 0 to 0, we go from 0 to large value and then to 0. And for a phi parameter, instead of going from 0 to large value, go to do it also in steps like this. So the point is that now this part looks exactly like this, but in the mirror theory. So this part really computes us the half index with a thimble boundary condition. So I can write this as half index in the dual theory with a boundary condition labeled by beta. So beta is what vacuum we find here. But now we also have these two interfaces, which after we look at it, we see that they're just our Januses. So we get there's a Janus that switches the phi parameters, and then there's a Janus that switches masses. So we sort of reach at the same conclusion, but in a slightly different way, that this interface relates half indices. But now we look at them in the sort of original theory and the mirror theory, and we see that one has to multiply by this matrix to relate the basis, on the left and on the right. And okay, one small remark. Then whenever I write that this mass is really large, or a phi parameter is really large, so what I mean is that they're taken to infinity within a chosen chamber, of course, because there's a chamber dependence. So the picture is like this. So I choose some value and then send it to infinity within this chamber. Okay. Now, let me move to the next topic, namely we'll discuss, relate this to various cohomology theories, or sort of relate to various cohomology theories of the Higgs branch. Are there any more questions at this point?
Well, yeah, I sort of elliptic or whatever other stable envelope, they have a certain definition. Is that obvious that that definition is the interface you write that satisfy that definition, or is it?
I think I was planning to say something about it, but not too much.
Or maybe I'll put it differently. Do you consider this to be the identification? Do you consider this to be clear, for some reasons that may stay outside of this presentation, or do you consider it to be expected or conjecture, or what's this identification that how we should think about it?
I think it's, strictly speaking, it's expected and conjectural.
Uh-huh.
No, because these BPS equations are the gradient flow equations, which give you exactly this attractor submanifolds. It suggests that it's the same thing.
Okay.
And one can do some computations, and whenever you do computations, the answers agree, but up to normalization.
Okay.
So this really gives you sort of more, looks like it gives you more of a thing, more what you call the pole subtraction metrics.
Uh-huh.
Differs by normalization, which is of course suggested by this relation, the two vertex functions.
Okay. All right, super.
Okay. Now recall from last week that once you have the supercharged Q and you take its anti-commutator with Q dagger, then you get it, at least in this case, a Hamiltonian. So the Q cohomology, as I said, is a space of supersymmetric vacua. And in the one-dimensional case, in 1D, it's well known, of course, that this can be identified with a Aquarian cohomology of your X H. And if you look, start with our GLSM description in the Higgs phase, and then flow to low energies, and you get some effective description by a nonlinear sigma model into the Higgs branch. And in the NLSM case, it's a classic result, of course, due to Witten from the 80s, this supersymmetry and Morse theory paper, that we know that in quantum mechanics, in supersymmetric quantum mechanics, the Hilbert space, okay, here I write as the Hilbert space because it's associated to a point, right? In quantum mechanics, it's just this space of differential forms on your Higgs branch, on your target, completed with respect to some with an L2 norm, and then Q and Q dagger are just the RAM differential and the dual, or in the equivariance case, we also include contraction with some vector field. And then the dual is, what is it? I think it's, you take the corresponding differential form and then do this. So the Q cohomology in this case is just the de Rham, or in the equivariant case, equivariant de Rham cohomology of your Higgs branch, or your target manifold, or you should take some L2 cohomology, the non-compact case. But now once you lift to 2 dimensions, the HT, the cohomology should be lifted to the equivariant K theory. And there's some independent arguments, but from this point of view, one can think also of the 2D theory. So we have a 2D theory on the cylinder instead as a 1D theory. So we consider this NLSM into the Higgs branch. Instead, we can think of it as a 1D theory into the loop space. And in our supercharge in 2 dimensions, whereas a base squares to, so one thing is the loop rotation, and then there's also some, well, it's different mass. Let's just call it M. it's part of the complex mass in 2 dimensions. So the previous discussion, namely the one in the quantum mechanical case here, suggests to identify the Q cohomology with rather the equivariant cohomology of a subspace of your X, equivariant with respect to loop rotations. And okay, so here, like in the shows, there's a little audience participation time because I couldn't find any precise statement in the literature, but maybe it's something well known, but because there are like some hints that it might be. So is there any precise way to relate this equivariant cohomology, equivariant with respect to loop rotations, to the K theory of X?
Yeah, well, we'll send you maybe some links later. There's some ways there's some authors who talk about it.
Okay, yeah, that will be helpful.
Yeah. Unless somebody is ready to provide reference in real time. Yeah, maybe it's okay to postpone this.
Mhm. Yeah, so one can sort of course, relate this to, like, by a localization argument to, I guess, to cohomology of constant loops, which becomes just this. And then since we're working on over complex numbers anyways, these things as vector spaces, there's the same, but if there's like some natural way to relate them, then that would be helpful. Now we can also further lift to 3D, and then there's a similar story. In this case, the as I said previously, the supercharged squares to the anti-holomorphic translation, and then this 3D NLSM into the Higgs branches, like a 2D NLSM into loop space with extra equivariance with loop rotations. And in this case, okay, there's an analogous question. And in this case, I've even seen Andrei writing formulas like this. So again, if you can send me some references, would be helpful. Because I was able to find something in the literature, but I have a feeling that that's not the right place to look what I found. But anyways, there was a little bit of section showcasing my ignorance. Now let us take instead the perspective as in work of Aganagic-Okounkov, namely so we'll think of this as a scheme over here. We have this torus of flavor symmetries mod the Q to the lattice of co-characters. Or equivalently, these are the flat flavor connections on our elliptic curve, or equivariant elliptic parameters. Now, if for generic equivariant parameters they're only isolated massive vacua, then this scheme can also be understood as the classical description of these vacua. So how this works, we have these equivariant parameters. Recall that in our case we have, let's call little x the parameters for n equals 4 flavor symmetry, and h bar is this parameter for special U1, in this case, complexified C star. And then there are also gauge parameters or turn roots, which we can also think of as living in E sub h. This is analogous object, where by h I mean the maximal torus of our gauge group. So physically they're of a similar nature, x and h. The equivariant parameters are flat connections for the flavor symmetry on the elliptic curve, and this s or flat connection for the gauge symmetry, the maximal torus of the gauge symmetry. In each massive vacuum of our theory, S adjusts itself to a certain value, which cancels some of the equivariant parameters and allows for matter fields to have Vev corresponding to that vacuum. So in that case, you get this sort of picture of a classical spectral manifold where, and okay, yeah, so on the vertical axis, we have this parameters, the gauge parameters. On the horizontal axis, we have this flavor parameters. And then each irreducible component here corresponds to a massive vacuum. And this graph is the this scheme LT of X. For example, if we have like n equals 4 super QED, so that's just a U1 gauge theory with n hypermultiplets, whose Higgs branch is T star CPN minus 1, then this scheme is just given by this equation. Well, this equation really gives you the spec of K theory, but then L elliptic is obtained by taking mod Q of it. Okay, there's nothing really new here. It's just something that I learned from Andrei's course. But the point is that from physics point of view, there's just the classical description of massive vacua for fixed points. Just this, like for each value of equivariant parameters, you have some set of vacua that sit on top of it, and then you start changing parameters, and the vacua change. Now, in quantum case, vacua are not just some values of fields, they are states, so elements of the vector space. So in this picture, so I just copied the same picture. The points 1, 2, 3, they correspond to one-dimensional vector spaces, so just spanned by the corresponding vacua in the quantum world. And together they add up to a certain bundle, vector bundle over this base. But now also notice that here I replaced ET, so this space that parameterizes equivariant parameters, by something else. So I just included one more factor, and the same, the elliptic homology got replaced by this product. So this additional parameter space is just a space of Kähler parameters. So physically, so of course this is how it was done in Aganagic-Okounkov, but physically these are flat connections for the topological symmetry on the eta. So recall I told you earlier that in gauge theories, when for each abelian factor of the gauge group, you can introduce this topological current. And they really must be included in the quantum case, because so the classical physics doesn't see them. which is why in this picture we simply multiply everything by this additional scores, by this additional space of parameters, and this picture doesn't really change because that's a classical picture. But in quantum case, when we are talking about this space of vacua, they must be included because non-perturbative effects coupled to these parameters. So I should say that because non-perturbative you get some vortices and monopole operators that are charged under this topological symmetry. So these non-perturbative effects introduce dependence on the Kähler parameters. And so here I said that there is a certain bundle of vacua. So to each point, one associates a one-dimensional vector space, and then together they add up to this bundle. But in fact, it's better to think of a line bundle on what is it? On this ET of x, which is LT of x times this ET prime. And then the bundle of vacua is just a push forward of this line bundle with respect to this map, since we have this ET of x as a scheme over this space, we can take a push forward. Now the question is, what is this line bundle? Its topology in quantum field theory is determined by the 't anomalies. So how do we think about it? Imagine that there's a half cylinder, which is, so here it's our elliptic curve times a half line. At infinity, we fix the isolated vacuum number alpha. And then we would like to read off the wave functional of the vacuum here at the boundary. So for that, we need to construct Hilbert space of the theory first, or at least construct in quotation marks. So give some description, because it's in the QFT case, it's of course much more complicated to do it rigorously than in quantum mechanics, where everything is well defined. But you do it in sort of canonical quantization or geometric quantization. And of course, here you have to pick polarization on the phase space of your theory. So the phase space here would be, you can think of it as if our theory was just about maps into XH, then the configuration space is the space of maps from the elliptic curve into XH. And the phase space is the cotangent of that, cotangent bundle of that. And one has to pick some polarization on it for the quantization purposes. But we want to do it in a supersymmetry preserving way because, well, we work with Q cohomology. We want to preserve Q. And fact is that the n equals 2, 2 invariant polarization on the phase space, so on this infinite dimensional space, which is a cotangent of the configuration space of your theory, it can be constructed based on the choice of polarization on your XH, thought of as a holomorphic symplectic manifold. Well, really, since I should say that since we're working describing this in the GLSAM language, then really we want L polarization on this linear space T star R, which we start with in the hyperkähler quotient construction, but then it also gives you a polarization on the Higgs branch. Let me call this one L sub H. But then L is polarization on this space. And that's really the physics origin of appearance of polarization in the construction of stable envelopes. Because when I say that there's this Janus interface and it maps between vacua, it's all well and good, but once you get slightly more concrete, you need to describe your Hilbert space, and it turns out that you need to pick polarization.
Mykola, this is super interesting. But say, is there some quantization of X somewhere in this? Is or it's you're not quantizing X somehow, or is that, or are you?
No, X is not quantized.
X is not quantized, right? No, it's
right.
Okay, that's just because it's, of course, quantization of X is another thing where you really would like to use the polarization, but that's not okay.
Right. Yeah, so you're really quantizing the phase space of your theory, which has, say, in the simplest case, T star of the space of maps from ET.
Okay, okay. Oh, so you quantizing something like the maps to X, is that roughly? No?
T star of maps to X.
Right.
Because
okay. Oh, and even for that you need the polarization. Like you don't.
Yes.
Okay.
Yes, because that's so that's in quantum mechanics or in quantum field, how it always works in quantum mechanics, because you essentially your quantum theory quantizes the phase space of the classical theory.
Okay. All right.
But yeah, but here the so the fact that I didn't explicitly so this fact that I didn't explicitly explain but just said in words is that the supersymmetry relates you so in quantizing, you for each scalar field, you're picking what either you fix its value at the boundary or its normal derivative at the boundary. And then your wave function or wave functional depends on these boundary values. But if you want to do it in the n equals 2, preserving way, it turns out that for fields that correspond to this polarization holomorphic symplectic manifold XH, for them, you fix their boundary values. And for the fields that correspond to orthogonal directions on XH, you fix the normal derivative at the boundary.
Oh, okay.
So that's it.
So it's more like replacing the need to have some sort of Lagrange in the next, right? It's some way to Okay. All right.
Now, here, just to give you a flavor of it, because it's really trying to work out the details right now, so it's work in progress. One can do some computation based on anomalies and find that this bundle L has roughly sections of form like this. So there's some part that corresponds to polarization. There's a part coming from vector multiplets. Then there's this non-perturbative part that captures the Kähler parameters. But the point is that it's supposed to be basically fixed by anomalous. And by anomalous, I mean anomalous at the boundary, because really, if you're talking about perturbative anomalies in quantum field theory, they only exist this perturbative anomalies only exist in even dimensions. So in this case, we are in 3D, so there's nothing in the bulk, but there's certain anomaly at the boundary, and it determines you the topology of this bundle of vacua. Now, let me move to the next section, which is the effective description of 2D effective description of these stable envelopes. So consider the mass Janus that interpolates between zero mass here and a mass that is very large, and we actually take it to infinity inside the chamber C. This sort of realizes you the so of course physically it's clear that it gives you a map from, you either look at from the left to the right or from the right to the left. If you look at from the right to the left, it gives you a map from the vacua at large mass to map of the vacua at zero mass, and then this vacua should correspond to sections of this bundle, either over the fixed locus, because that's the Higgs branch when the masses are turned on, or to the entire or for the entire XH, because that's the Higgs branch when there are no masses. And then, as I said earlier, BPS equations, the gradient flow, the similar thing that appear in the mathematical constructions of stable envelopes. So we expect that this would be the same object of the normalization. And well, I don't want to overstate, but it probably can be proved in some sense based on the list of characterizing properties of stable envelopes.
Yeah, as soon as you know it's a section of the right bundle, then you're done, right? I mean, what's the definition? It's just a section of some bundle that is, uniquely defined by its the values it takes on some points.
Right.
The fact that it takes some values at some points, that's automatic, and that's the only thing to check is that it's a section of a bundle.
Mm-hmm. Okay, cool.
Which I guess it refers to your previous computation, which you set as work in progress.
That's right. Now, since mass is very large here in this part, really the gradient flow, it happens really fast. Like when the mass is finite, you can imagine that it takes infinite time to go from one fixed point to another. But if you take mass to infinity, then it happens really fast. You're going from one point to the next, and then if there is the possibility of the next flow, you can go to the next point, and then there's this sequence of jumps. So in this case, we don't really need infinite time, enough to consider an interval. So the citing is as follows. There's this slab. Sorry. There's this geometry where you have an elliptic curve times an interval. And again, there's half of the interval has zero mass and half has very large mass. And at the boundaries of the interval, we fix these special boundary conditions corresponding to vacua. And then all we have to do is compute partition function on this geometry. This leads to a certain effective 2D n equals 0,2 description. It's like you can take the elliptic curve really large and then look from far away, and it looks like you just get the two-dimensional theory, in fact, two-dimensional theory with 0,2 supersymmetry. on this elliptic curve. And then you compute its elliptic genus, and that gives you a matrix element of the stable envelope between these two vacua. And this is also a part that's in progress, but in general, one can expect to write formulas for stab in this case using this approach, and it works for things like T star CPN or T star Grassmannian. So just we will probably clarify all the details fairly soon. And last, let me very briefly mention about the R matrices, because now we can consider the situation where we changed mass from some value M1, large value inside the chamber C1, to some M2 inside the chamber C2. And the corresponding interface that changes these masses. Because we have this property that nothing depends on the mass profile, we can just split it as a two-step procedure where we interpolate between M2 and 0, and then between 0 and M1. And
I think you have the order of M and 0 in the one of the brackets wrong. It would be like M1 0, M2 0 or something, or the other way around. I forgot your notation. Oh, okay, you don't mean, sorry. You previously used this for things with both scalar and equivariant variables, so this is why it's I got confused. But this here just means two masses.
Just masses, yeah.
Okay.
Yeah, so here just so somehow this stable envelope for Higgs branch corresponds to just masses. But when you want to go between Higgs and Coulomb phases, you need to adjust both masses and
Yeah. So you just used some notation with two arguments back then, which is I think the same notation.
Well, I think
different meaning.
I tried to use J tilde for the 5-parameter one.
I don't think it's some material. I think as long as we understand which one we're talking about.
Okay. So in particular, for example, in the 1D QFT case, we get a map from the equivariant cohomological of fixed locus into the same space. But this is a non-trivial map because we rearrange masses at the interface. So they go. So there's this wall crossing happening. And one can actually find, so the interface in this case supports some trapped modes. It's known, for example, in physics that if you take Dirac fermion, so Dirac spinor in 3 dimensions, and turn on mass that changes sign at some 2-dimensional plane, then the 2-dimensional plane will support chiral fermion living there. So there are some fields, some degrees of freedom that gets trapped on this interface. And then one can, that's this part that I'm talking is also still to be, the details are still to be worked out, but it's kind of clear what's going to happen, that you can also compute matrix elements of this interface, and can be described as a QFT on the left and QFT on the right, coupled to this mode that's trapped on the interface. And one remarkable property is that such interface can sort of change the gauge group via the Higgs mechanism. For example, let's just consider this basic example for U n+1 gauge theory with L+1 fundamental hypermultiplets. So in this case, the Higgs branch is just the T star of the Grassmannian. And okay, there's a quiver theory that in physics notation is often written like this. where of course this is not quiver, it's a graph, but it's understood as an n equals 4 quiver. And to write the n equals 2 quiver, you replace each edge by 2 edges with arrows going in the opposite directions, and then you'll get the actual quiver. Now consider mass for a specific U1 flavor symmetry that just rotates the last hypermultiplet. In this case, there are L+1 hypermultiplet. We can consider a U1 symmetry that only rotates the last one. With respect to this U1 symmetry, the fixed locus is this. So there's just 2 copies of the 2 Higgs branches, but with theories whose gauge groups have different rank. Rank differs by 1. Yeah, so this is, in this case, at the QFT level, the mass, if we consider turning on mass for this symmetry and making it really large, then at low energies, it sort of breaks the theory into 2 subsectors. So this is the initial theory, and after you turn on mass, it breaks as a sum of 2 theories, like this. So this is actually, it's one of those rare cases when you get a direct sum of quantum field theories. And you can, of course, consider an interface for this mass where you change the sign. So in this case, then there's only one mass, there's only one wall in this space, which corresponds to 0 mass. And of course, this is an example. This example of T-star Grassmannian, where you can, when you take fixed points with this U1 symmetries from Maulik and Okounkov. And this leads to a certain 2x2 R matrix, or rather block matrix, that is 2x2 in this space corresponding to these 2 sectors, so sort of subtheory A and subtheory B. And this interface where the masses exchange, this allows to talk between these. It talks between these 2 subsectors. Now, yeah. So the point of this last part was really like I didn't really tell anything new except that just describe in sort of this physics language this example, but hopefully more will be in the upcoming paper or papers. And yeah, I think that's it.
All right, that was super, very inspiring. Questions? I asked plenty already, but maybe people have more.
Sorry. So what you described the Janus interface, the things, they work for 8 supercharges, right?
Mm-hmm.
And it all that basically it's like if you go to 4, then like Lagrangian theory becomes dependent on the profile of your like coordinate dependent mass or something, right?
Yes, that's right.
Is it still possible to make some kind of Janus interface for just for supercharges?
Yes, it's. I mean, it's just exactly what you said. It's gonna depend on the profile of mass.
But so, like, is it a dependence? Is it like discrete or is it like continuous? Or is it?
Well, I think it's continuous dependence. I'm not 100% sure, but so the thing is, in this argument, where was it? So let me see. Let me recall how it works. So the trick is this part where I say there's something vanishing under correlators.
Yeah.
Because even in n equals 2, see that you have some Q exact piece plus something which is proportional to, if we go technical, to auxiliary fields in the chiral
Okay.
multiplet. And in general, that's gonna be non-zero on the correlators, but in precisely in, so it will lead to some continuous dependence, but precisely in n equals 4 case, due to the special form of the superpotential, that thing vanishes. So I think it's going to be a continuous dependent, but that's only for masses. For phi parameters, interestingly, it's even
Well, I was more interested in like in a phi parameters, because in a phi parameters you have this, you have this this wall crossing as well, and but there you have this kind of, I mean, it kind of relates with what Andre asked like earlier. I think you have this kind of different paths along which you can continue a phi parameter and get some kind of monogamy.
Right. So so that thing is usually discussed in the context of the, like in the A model context, where the phi parameter gets naturally complexified by the theta angle, and there indeed there might be monodromies because there's like a complex codimension 1. There's probably some subtleties in this case as well, in the real case, in n equals 2. Probably them, life can't be as simple. I can only guarantee, sort of guarantee, that in the n equals 4 case, there are only walls, nothing else. But in n equals 2, I don't really know.
Yeah, thank you.
This actually relates to your the question we discussed with Kostya during his talk. And this is, if you want the sort of elliptic interpolation, you need conditions of the kind that, you know, not only some numbers have to sum to 0, but also their squares need to sum to 0.
Yeah, exactly.
That is so elliptic interpolation is a little bit tricky. So actually, I think it's very related. To what extent this can be, you can to which extent you can interpolate things if you go away from this n equals 4 situation. I don't know. I mean, I haven't thought about it.
Okay.
More questions?
Maybe a little off topic, but you said that 1D theories correspond to cohomology, 3D to elliptic. What happens in 4D, or what goes wrong?
So in 4D, this U1 H bar symmetry, it becomes anomalous, so it's not there anymore. So so this symmetry was kind of important in a lot of these constructions. You remember, I guess, what I'm talking about.
Yeah.
So this U1 H bar, it's part of the n equals 4 R symmetry. It lifts. So in 4D, so you can of course go to 4D n equals 2 in that case. So that's also a theory with 8 supercharges. In that case, the R symmetry group is SU2 times U1, and that's U1 part is usually broken by anomaly, unless you are in the situation of what's called sometimes balanced theory, or it will be conformal in 4D. So in that case, so it's like, for example, for if we have this UN SQCD, so UN theory with L hypermultiplets that corresponds to Grassmannian, T star Grassmannian n comma L. The balanced case is when L equals 2m. So so I guess the short answer that this whole construction breaks when you go to 4D, but there might be something special about these theories where the symmetry is preserved, and I don't really know.
But there are very few of them, right? This is, you can also see it from the kind of, you know, it has to be conformal or asymptotically free, and that means we're talking about some if in the language of some kind of quantum affine Lie algebras, conformal means it has to be the zero weight of some representation, and for most things, for most of the algebras we have here, it has no zero weight, or the zero weight is stupid, and so that's because this is we're talking about some high straight representation, some very big algebras, so that's typically the zero weight is not there, not present, or it's somehow empty, like if you for most quivers there's nothing.
Right. But then there is these special cases.
Yeah, the special case, but there's a classification, right? It has to be, it corresponds to like basically a finely algebra, and that's so it means it has to be not only it has to be a finite dimensional algebra plus very specific matter. So it's that's a many case.
Okay, thanks.
I had a question about the last thing you discussed, the very last topic, and then you said, so in that Grassmannian example, can you say a little more about this extra degrees of freedom that live on the interface? Or is there some way to somehow, say something about them? You said there's be extra stuff living on the interface, and that can we?
Yeah. So so the hope is that one can actually just explicitly identify these degrees of freedom, write Lagrangian for them, and couple them to the bulk. And one way to understand this also would be to do the following: to consider sort of split these things, because say we know that there's mass m1 here, m2 here, and then there's mass is 0 here. So just split it into like stable and like yeah. And then this place where the mass jumps from 0 to m1 or m2, so this the red interfaces, one can actually write down boundary conditions that are satisfied by your fields. I guess let me give you an example. If we have, say we have a hypermultiplet that let's call it H, a hypermultiplet that consists of a pair of chirals I and J, and let's say that the mass, or we consider U1 symmetry that U1 symmetry that rotates this one with charge +1 and this one with charge -1, and let's say that that's exactly the mass that we consider here. So the mass is -m here and +m on the right. Then in this case, one can show that the boundary conditions that are satisfied by these chirals will be as follows. Sorry. So on the right boundary, we have Neumann. Maybe it's too small. On the right boundary, we have Neumann for I and Dirichlet for J. On the left boundary, we have, so if we had +m on the left, we would have the opposite boundary conditions, but we have -m. It means that we actually have the same boundary conditions for I, because it matters whether you consider the right or the left boundary condition. And this already shows that here in the interval, in between the boundaries, there's a certain zero mode that survives, and I can actually describe the zero mode as a 2D 2,2 chiral multiplet. It consists of okay, sorry, I don't know, it might be so there's a 2D 0,2 so-called Fermi multiplet. Let's call it psi I, because that's no psi j. So that's the leftover from this boundary conditions, because they kill you the bosonic field but leave certain fermions on the interval. And this thing does the opposite. It kills part of the fermions and leaves you a certain boson. So you get also 2D 0,2 chiral multiplet I. And together these two fields form a 2D 2,2 chiral. So I don't know how familiar these notations and this language is, but the point is that in this example, one can actually identify zero modes that survive on this in this slab between the two red boundaries, subject to these boundary conditions. And then yeah, like once you know the zero modes and the charges and they're coupled to the gauge fields, then you are in business. You can do computations with them. So it's stuff like that, but then in more complicated cases when you have more than one hypermultiplet and some gauge fields.
Okay, and so and then presumably something like that. I mean, can we suppose we're well, maybe let's say in the three-dimensional situation, so you'd be able to compute the precision function of those zero modes from some kind of pose of the R matrix. So that would be roughly the computation, or is that not? It's not going like that.
I think it's the other way around. I can compute the partition function, and that gives me the matrix elements of the R matrix.
Oh, okay, okay.
Because there are methods in physics how to compute such things.
Okay, all right. Okay, makes sense. Well, more questions? Well, if there's no more question, let's thank Mykola. That was really stimulating discussion, and we'll be looking forward to these upcoming papers that are you mentioned right before your very eyes and your own eyes, and so then to be continued. And then next week it's Henry. So thanks everybody.
Thanks a lot.
Yeah, thanks.